Okay, I'll start a little earlier than I thought because I was able to get things set up. So anyway, welcome back. As I mentioned last time, we've basically exhausted the material of the course, and so what's left is the remaining fun stuff that I wanted to do. The remaining fun stuff I wanted to talk about, one is the Jordan canonical form. The other is the Hadamard matrix conjecture. So I will talk about both of those. But first, at the end of class last time, we were talking about we were actually discussing this application of the SVD to image compression. Okay, and so just to remind you what I was saying last time, this was my setup. So the idea is that I take an image that that I think of if I'm storing the, say, color data for the image, pixel by pixel. Then if this is a 200 by 200 pixel image, this would be contained in a 200 by 200 matrix. And so this is giving you a couple of ways in which you could do this. So you could do something really simple where each entry of the matrix is either a 0 or 1. So it's 0 if it's black and it's 1 if it's white. If you had a grayscale image, you could do a similar thing, except 0 is black, 255 is white, and then in between is, you know, some shade of gray in between. Okay. Now, the idea as I mentioned last time, is the SVD allows me to look at this image. If I take the SVD of the image matrix, I get a bunch of singular values. Recall what those singular values corresponded with when we were talking about the SVD. And recall that, you know, the tie-in with constrained optimization, where the largest singular value told you something about maximizing a value, a certain length in a direction, right? And that direction was given by the corresponding eigenvector, and the length of that, right, was actually given by the singular value itself. That's actually what the singular value was doing. It was the length of the original matrix. We started with A times that eigenvector, and so the idea here was that I could do this analysis. I could take SVD of my image matrix, and it allows me to show which is the important data. That is, which part of this matrix contains maybe the most efficient data, and which part contains data that's maybe not as efficient. And so I could concoct an example where my singular values are kind of evenly spread out over this matrix. That's not typical, however, right? So typically, the singular values, you have a few that are much larger than the remaining ones, and then eventually, you know, they will zero out at some point. That's kind of the more typical picture of what happens. And so anyway, let's see an actual example of how this works and what it means for what's going on here. So suppose I have I have a 200 by 200 image. So corresponding to this, I have a matrix that is a 200 by 200 matrix. Okay. All right. And so let's suppose that I have 200 singular values. All right. So I mean, well, let's not suppose. This is how many singular values I have. So singular values for this matrix. Well, if I listed them out, right, this would be sigma sub 1, sigma sub 2, and so on, all the way out to sigma sub 200. Right. Okay. Now, what is if I make this idea a little bit more rigorous, so idea made more rigorous. So this is just the idea from above that I'm actually putting some, precise words here. The idea is that these singular values tell me the important directions. Okay, so singular values tell me the most important directions. And maybe I need a quote within a quote here, but I won't do it. For directions. Okay. Thus, tossing out some number of the smallest ones tossing out some number of the smallest ones lets me reduce the amount of data I need to generate the image. And by tossing out, that means I would then zero out in the corresponding SVD. I could actually zero out the columns that are associated with those singular values, right? So when I say tossing out here, so tossing out means I would ignore those singular values and use a smaller matrix, basically, where I've just gotten rid of those extra columns that we know are associated with singular values themselves, right? So that's the idea. Okay, so I will toss out some number of the smallest ones and the associated column vectors in that decomposition that go along with them. That's why this allows me, because you might ask, like, how does this allow me to reduce the amount of data? So reduce the amount of data, right? Maybe this is an aside. So how? Well, I can use my new SVD, right, to find a new A. Right, maybe I should put my quotes here, right, which contains less data. That's the idea. Okay. If you're wondering how you go from tossing out singular values, how does that save you any data, since, you know, the matrix that you started, like if you just ignore the singular values, that doesn't change A in itself. So when I say ignore the singular values, I mean in the SVD, you actually remove those singular values and then get rid of the corresponding rows, so that the matrix you get going backwards, right, now multiplying out the SVD to get some new A that contains less data. This new A you get out of this process contains less data. All right. Okay. So that's how this works. All right. Now the main thing I wanted to show you here, not actually going to do like a real example of this, because it would take too long, and it would require, really, when you're doing any of these kinds of I mean, it's a 200 by 200 matrix, right? So I would just be using MATLAB to generate the output anyway. But the idea here is to show you exactly what is meant by things like image quality, and exactly how much how much fidelity of the images is maintained by tossing out some. So let's say, maybe I'll save my blank fun stuff page for later. Not saying that this isn't fun stuff, but let's say that I only want to keep the largest 50 singular values. So those singular values are sigma 1 to sigma sub 50. Okay, so let's say that I have a good feeling that if I keep 50, right, out of the total 200, right, so out of the total 200. Another way of phrasing this is that I would be dismissing, right, or tossing out the, I'd be tossing out the lowest or the least 150 singular values. Okay. All right. So the question becomes, how can I tell? So how can I tell how good of an approximation the resulting, we'll call it A prime, and thus resulting compressed image. That's the compressed image associated with this new matrix A prime. So how can I tell how good of an approximation the resulting A prime is? Right. Of course, really what I'm interested in is this resulting compressed image. And the answer to that is I can compute the image quality directly, so I can compute image quality as a proportion of variance. So I'm not going to define it, but if you have seen variance in a statistical sense, then you'll see what thing I'm doing here. So the idea is I take the sum of the squares of the singular values I've kept, okay, I take the sum of the squares of the singular values I've kept, and I divide by the sum of the squares of all the singular values. Yeah, and as Gustavo said in chat, this is what I was saying when I was saying, how can you determine how much fidelity has been maintained? So this is going to give us a numerical value. I'm going to divide by the total sum of the squares of all singular values. And so what this is, in another way, is to say is that basically I have my variance of the image that I'm going to get after tossing out all but the top 50 singular values, and I'm dividing by the total variance of the original image. And I'm not going to get into, like I said, calling, I'm not going to even define variance, but I'm just going to call these things that. Okay. And so, let's say, for instance, so, if you're watching and you are curious as to what comes next, I'm just going to make up a number here. Okay, so I'm just going to make up a number. So let's just say that this is, so I'll maybe even write this. So say that this is equal to, when I actually compute this, let's say that this is equal to 0.9997 and so on. Okay. I'm getting this from part of an example from the Math 401 textbook or Math 401 online notes. Okay. So anyway, then what does this mean? So what does this mean? So what this means is that we have basically preserved 99.97% of the original image variance. So we've preserved 99.97% of the original image variance. Okay. And we'd say, so loosely speaking, the resulting compressed image is 99.97% as good as the original. So the resulting compressed image is 99.97% as good as the original. Okay. Yeah, so right. So people are asking basically what you would do in terms of picking, what it is that you want to do. Yeah, so like if you're to go kind of in the opposite direction, right? If you basically specify an image quality that you're happy with, then yeah, you could actually find, however many singular values you need to keep that you think. But and yes, Yekta, you do this to take up less space because the resulting thing, like, look how many singular values you've tossed out, right? You've tossed out 75% of them. Okay, so you can compute how it is that you have done this, the amount of the amount of the amount of data that you've saved. Let's see. What's the quickest way to do this? So if let's see, if I preserve, let's say that I have n. Yeah. Okay. So let's go ahead and do this as to show how much we've saved, right? So, like I said, this is loosely speaking, and there will be examples of that can be concocted where this the image quality is seemingly high, but the image looks like trash. So this can be a little sensitive. So don't. That's why I said loosely speaking here. Don't think that it that 99.97. Yes, that's a good image quality, but like I said, you can construct examples with like 90% image quality, but the image is like pretty dramatically degraded. Okay, so and that's why I'm saying loosely speaking, because the way the image looks really ultimately the way the compressed image looks can really depend on like the particular image itself and that particular matrix that you start with. So anyway, let's do like how much data did I save, right? How efficient am I being? So how much data do I save? So there's you can think of the following value. The idea is I can write up a compression ratio, which is if the matrix I start with is an n by n matrix, that is I have n singular values, right? And I preserve k of them. All right, so preserve k of them. So then there's an argument I can make for why this compression ratio is actually telling me how much I've saved space. So my compression ratio is 2nk over n squared, right? And of course I can simplify this to just being 2k over n, right? And note if 2nk is less than n squared, I've saved space. Okay. So this is my compression ratio, which I can compute in that example. So in that example that we did, n is 200 and k was 50, right? Okay, so 2kn is 20,000. So this is 2 times 50 times 200, which is 20,000. Okay, and 200 squared is 40,000. Okay, and so our compression ratio, right, 2kn over n squared is 20,000 over 40,000, which is 50%. Okay. So there's a computation behind this that kind of makes that make a little bit more sense. But because I want to get to other stuff, I'll move on. Yeah. And so so the idea is this is one tiny application of SVD. If you take Math 401, I can just quickly look. So looking at the notes for SVD, there's like a good 20% of the chapters, right? So out of the first 15 chapters, which are mostly what's covered in the course of Math 401, like 1/5 of those chapters, a little bit more than that, is based purely on applications of the singular value decomposition. So there's tons of stuff that this can do. Our textbook also mentions some applications, but I found this one a little bit more interesting. Okay, so that's that. Okay, so now on to something completely different. So fun stuff. I mentioned that I would talk about the Jordan canonical form. That's the first thing. So Jordan canonical form. So this is JCF. Sometimes it's the Jordan normal form. I prefer Jordan canonical form, but it doesn't really matter. Everyone will know what you mean when you say this. Okay, so the way that this, maybe the best way to do this is just work out an example. And actually, this example is straight from the Wikipedia page for Jordan canonical form because it's a really good example. So let's look at the matrix A. Okay, so the matrix A that I'm going to look at, reading row-wise, this is 5, 4, 2, 1. Second row is 0, 1, minus 1, minus 1. Third row is 1, 1, 3, 0. And last row is 1, 1, minus 1, 2. Okay, so what are the eigenvalues? So eigenvalues of A are 1, 2, 4, and 4, listing with multiplicity, right? Okay, so 4 has algebraic multiplicity 2, but the dimension of the null space of A minus 4I is 1, right? Which is not 2. What does that mean? I'll give you a little bit in chat to tell me what this means. So I have a 4 by 4 matrix. It has eigenvalues 1, 2, 4, and 4. Listed 4 here because it has algebraic multiplicity 2. But the dimension of the eigenspace associated to the eigenvalue 4 is 1, not 2. Okay, so it's not diagonalizable, right? So that's what chat says, and that is right. It's not diagonalizable. So A is not diagonalizable. Okay, so our hopes for diagonalizing this matrix are dashed, right? Now, yeah, as chat also mentioned, we developed the singular value decomposition as kind of sort of this pseudo-diagonalized thing. Now, it wasn't really, right? It was not it was not as nice as we hoped, right? It wasn't super duper similar to diagonalization, and it, of course, it's nice for a variety of reasons, but it's not the same because the matrices U and V, for instance, were different matrices, right? For diagonalization, right, what we had is that our matrix A is equal to, P, D, P inverse, right? That's what we had, right? So we had an invertible matrix P that diagonalized this matrix. And the reason why that's so much nicer than an SVD conceptually is that we know that this matrix P is actually like a change of basis matrix. And so really the strength here was that we have a matrix A. It is, say, of this form. If it's diagonalizable, right, then we could change basis using this matrix P to a basis where this matrix was diagonal. That was what was so nice. But if it's not diagonalizable, we can't do that. The SVD has a lot of nice applications, but the SVD, right, is this thing, right? And this is fundamentally different. I can't change basis where A is this sigma, really, right? I mean, I can, you can kind of say I've like changed like half of the way, right? I've done it on the left or on the right, but it's not really the same thing that's going on here. And so I'm going to ignore that. This is still true. I can still do this, but I'm going to ignore that. Okay. So it turns out that there is an almost diagonal matrix J such that there exists an invertible P such that A is equal to P J P inverse. This J is called the Jordan canonical form. Of A, or JCF. All right. And there are Jordan canonical form calculators that you can use for some matrix. Okay. Now, here's the thing. Again, what is so nice about this compared to SVDs we were just talking about is we can change basis, right? Using this matrix P, the columns of P form a new basis for the space we're working in. And in that new basis, A is represented by J, right? So A gets mapped to J by that change of basis transformation. And so J is what we can work with instead of A. We couldn't really do that with the SVD, right? The SVD was nice computationally, but it wasn't nice for this kind of stuff. This is so nice that basically, when you're doing any higher linear algebra, so if you take any more advanced linear algebra, if you learn anything more advanced in linear algebra, if you keep going in this stuff, the Jordan canonical form is so nice that basically whenever you have it, you just assume your matrix is already in it, okay? Because pretty much anything that you want to conceptually do with a matrix is nicer if the thing is in Jordan canonical form. Actually, this Jordan canonical form is the diagonal matrix D if a matrix is diagonal. So even better, so or I should say, if a matrix A is diagonalizable, then J is equal to D. So diagonalization is a special case of putting something in its Jordan canonical form. Okay. Okay. So what is the Jordan canonical form for this matrix? Let's bring the matrix back. So here's my matrix A. What is the Jordan canonical form for this matrix? So for this matrix A, J is the 4x4 matrix. That is row-wise. I'm going to do diagonal first. So diagonal is 1, 2, 4, 4. There are zeros everywhere. Except here I didn't put a 0. Why? If I put a 0 here, then J is a diagonal matrix, and I would say that A is diagonalizable, but that can't possibly be the case, right? Because A is not diagonalizable. The dimension of the eigenspace for that eigenvalue lambda equals 4 is not right. It needed to be 2, but it was only 1. So that's not a 0. Well, I'll just make it a 1. And that's it. Okay. You can check. So there exists an invertible P such that A in our example is Pj, P inverse. And this is the Jordan canonical form for that matrix. Okay. Now, how do I actually define this thing? So how do I define it? So let me move on past this example, although I'll return to it to show some decent notation here. Okay. So I got a question in the chat. How do I know that the term is that term is the non-zero one? Right. So good question. So this one is the non-zero one because it is the one that corresponds to the eigenvalue that screws everything up. Right. So right, Gustavo. It's because that is the eigenvalue that was short on multiplicity. Right, or it was short on the dimension of the eigenspace, right? So dimension of the eigenspace for that eigenvalue was 1 when it should have been 2. And on account of that, I had to have this 1 here. I can't have a 0 there because then J would be diagonal and it'd be no good, right? Okay, so then what happens if you have an eigenvalue that has multiplicity 2, 3, 4, whatever, but the dimension of the eigenspace is fine? Well, in that case, you get a block in the Jordan canonical form that would have repeated copies of that eigenvalue, but would have zeros instead of the ones above the diagonal. Okay. So how do I define J? Maybe the best thing to do, rather than write out something, I'll just write out, a big, huge block. So a Jordan canonical form is made up of blocks. Okay, so it's not diagonal, but it is upper triangular, right? So note J is upper triangular. So that's always going to be the case. Okay, these Jordan canonical forms are defined to be upper triangular. All right. So how do I define J? The idea is I do the following. Maybe for a repeated eigenvalue lambda 1, I have 1s here. It doesn't matter what is outside those. This picture is also on the Wikipedia article for those that are interested. On the diagonal, maybe lambda 2 is repeated twice, so there is the block associated to that thing. Maybe lambda 3 is a simple eigenvalue, so there's the block associated to that thing. And so on, all the way to lambda n being repeated twice and having that last block there. If the multiplicity of some lambda I is equal to the dimension of the eigenspace, okay, then the associated block is lambda I, whatever your multiplicity is, and then zeros. All right, and of course there's zeros below. Okay. So in this way, when you actually write out this thing, this is a direct generalization. Actually, well, okay. I mean, okay. You don't have to do it this way. So in fact, for reasons that might be nicer, actually, maybe you shouldn't call this the block. So you could actually split this up into these sub-blocks. Well, does it matter if yeah, no, I think it's fine either way. So you could consider each of these separate blocks if you wanted to. That way your block always has the ones versus these which don't have the ones. So maybe that's a better thing for what you want to say. That way your blocks always look the same. Yeah, in fact, yeah, you should do that instead. So so maybe I shouldn't say the associated block. I should say what it looks like is this. So then I split up all these into just the separate eigenvalues. So I can have repeated eigenvalues that are contained in these blocks, but if I block them together in this way, when the eigenspace doesn't match up in dimension, then yeah, I'll call these the Jordan blocks. So these are Jordan blocks, and I won't call this thing a block. Maybe I should. Okay. Now, we didn't really talk that much about block matrices or partitioning matrices, but the idea here is, so really the one time we did this was with the SVD, right? With the SVD, we formed sigma in the SVD was a block matrix where you stuck the matrix D inside of it and then you filled it out as you needed to with 0 rows and columns. Okay, so here you have a few matrix blocks that you're sticking inside a larger matrix here and then making the dimensions match up. Okay. No, Yekta, this is not going to be on the final exam. So Jordan blocks won't be on the final exam. Okay, and so this is what it looks like. For actually going through the process of doing this, I mean, I imagine that if I gave you a matrix that had nice eigenvalues, that you could actually do this, no problem. So anyway, with some minor, I should say, if I give you some minor guidance here, I think you'd be fine here. So anyway. This example is actually fully worked out on Wikipedia. So the example we did is fully worked out on the Wikipedia article for Jordan canonical form. So the example we used is fully worked out on the wiki article on JCF. So if you want to have a look at those computations, you can. And it also introduces the notation of thinking of it as a direct sum, which I'm not going to get into, but it's fairly straightforward. So anyway, so that's that. That is the Jordan canonical form. Why does this work? Sam, so another question you could ask that's similar is, when does this not work? So unfortunately, you can't do this for every matrix, right? So maybe I'll ask a question. When can I not do this? And the answer is when any eigenvalues of A lie outside the field of entries. So for instance, complex eigenvalues lie outside R. So complex eigenvalues lie outside R, and so here again, complex eigenvalues kind of infuriate us from one way. because not only can we not diagonalize them, we can't even technically put them in Jordan canonical form. Now the reason for that, of course, is that Jordan canonical form it wants to stay in the same field that the entries of A are in. Okay, and so really the only problem is that I can't slap complex entries into that matrix J. So if you're willing to do linear algebra over C, over the complex numbers, then you're fine, right? Then you're perfectly fine in that case. Okay. So in that case, everything works out, and you get Jordan canonical form for complex matrices. So this is a notion. If you have a field that is something, it's called algebraically closed. Algebraically closed means that any polynomial with entries or with coefficients in that field have roots that always are also in that field, right? So the reals are not algebraically closed, clearly, because you can even, right, like x squared plus 1, right? That's the coefficients there are 1, 0, and 1, right? So they're even integers, right? So even polynomials with integer coefficients don't have real roots necessarily. So yeah, in general, real coefficient polynomials don't have real roots, so the reals aren't algebraically closed. Complex numbers are algebraically closed. This is called the fundamental theorem of algebra. So fundamental theorem of algebra states that if you have a polynomial degree, so fundamental theorem of algebra says you have polynomial degree n, then counting multiplicity, it has n roots, right? And so if you don't care about specifying real versus complex, it's got all n of them. And in fact, more than that, if you have general polynomial that has, say, complex coefficients and its degree n, then you have n roots, and this thing factors completely over the complex numbers. Okay, so it factors totally. So that's fundamental theorem of algebra, some version of it. Anyway, so if you choose a field that is algebraically closed like that, then you're good to go. R is not, so that's why we have these issues here. But if we're doing it over C, then it'd be fine. Okay. So I have a little bit of time. I might have to dip into this a little bit on Friday. But I wanted to at least mention this just because it's fun. And that is the Hadamard matrix conjecture. So maybe I'll do it on the next page. So Hadamard matrix conjecture. First, before I can state the conjecture, I need to actually define what a Hadamard matrix is. So quick definition, a Hadamard matrix. So a Hadamard matrix is an n by n matrix whose entries are either +1 or -1, and whose rows are mutually orthogonal. Rows, not columns. Its rows are mutually orthogonal. Okay. And so these came about because the original problem being considered was what types of matrices had a maximum determinant under some conditions, and it turns out that these Hadamard matrices are the ones that do. And so I'll mention that later, but let's look at an example. So here's an example of a Hadamard matrix. I'll call it just H. So we'll do a 4x4 here. So the first row is all ones. Second row is 1, -1, 1, 1. Wait, What's going on here? Oh no, that's the wiki. Something's wrong with how wiki is rendering on my computer. It's like ignoring a couple of these. So both of these need to be -1. And then the third row is 1, 1, -1, -1. And the last row is 1, -1, -1, 1. Okay. All right. And so you can check that any two of these rows are mutually orthogonal. Okay. But it turns out that if I ask you to just come up with a Hadamard matrix, this is not as easy as it looks, right? So it turns out it's hard to come up with these examples. So it is very hard to come up with these examples. Now, there are methods that generate infinitely many of them, so maybe I shouldn't say very hard in that way, but it is very hard in the sense that, especially if I specify the size, this is a very hard problem. So it is very hard to come up with these examples. What's one thing that you might notice, right? So what's one thing that you might notice is true about this? So is any size allowed, right? So question, is any size n by n allowed? Okay. Yeah, right. So 5 by 5s are not going to exist. 3 by 3s are not going to exist. Why? Yeah, that's an issue. So odd by odd is an issue. The only example is a 1 by 1, which is going to be vacuously a Hadamard matrix, right? Just the entry 1. It is mutually orthogonal because there's no other row, to dot it with. So and so that does it. But that's not very interesting. The 2 by 2 Hadamard matrix is easy to come up with an example. In fact, you can see it in that example there. 4 by 4s you can come up with. 3 by 3s though don't work, right? And the reason they're not going to work is just simple. If these things are made of 1s and -1s, right, then how can you can't add, right, 3 plus -1s and get 0, right? So that's not going to work. But actually, it's worse than that, right? What about 10 by 10s, right? So clearly odd by odd is no good. All right, so for instance, for 3 by 3, you would have plus -1, plus -1 plus -1, I should say. Maybe I'll write it. Now, I shouldn't write it like that because then it looks like here. Let's not use any parentheses. All right, this can never be 0, right? So that's no good. Of course, when I write this plus minus, I don't mean that these all have the same corresponding thing. It just means they can be either one, right? That's no combination of those can be 0. Anyway, but also, what about 10 by 10? What about like 10 by 10? That's even. Is that okay? So powers of 2 are fine, but that misses out on some stuff. Okay, that misses out on some stuff. So if you think for a second, like what type of cancellation might have to happen, you'll figure out just with some basic algebra that it's multiples of 4 are what you need. Okay, so 10 by 10 is no good. But 12 by 12 is fine. Okay, so multiples of 4. So it turns out if H is a Hadamard matrix, then N is equal to 1, 2, or 4k for some k, i.e. is a multiple of 4. Okay. Yeah, exactly, Gustavo. It's because they have to come in pairs to cancel each other out, right? In some way. And so, like I said, if you work through this quickly, you will see exactly that must occur. So anyway, big question. So Hadamard matrix conjecture. Is that there exists a Hadamard matrix of every size 4k by 4k. Okay. This is unknown, so this is unproven. Or I should say unsolved. Okay. In fact, it took a long time for people to even come up with respectable size Hadamard matrices. So it was in the 60s, I think, that they came up with a 92 by 92. So I will go over some of these constructions at the very beginning of class. Next time, it won't take more than like 5-ish minutes. So a 92 by 92 Hadamard matrix was constructed in 1962, which is, in terms of math, that is insanely recent. And in 2005, so a 428 by 428 Hadamard matrix was constructed in 2005. Right now, the smallest Hadamard matrix for which there's no construction known is 668. So it is currently unknown if there exists a 668 by 668 Hadamard matrix. All right. So yeah, this is an open problem, and I'm not sure how much progress has been made on this since 2005. But it turns out that this kind of stuff, it seems like a really, really simple thing, but constructing these things is very difficult. You might ask, like, why would you want to construct a Hadamard matrix? So they have a lot of applications that I don't really know that much about. Eric asks, why do people use processing power in finding these arbitrarily large matrices if you can't? This is the type of thing that you can't, necessarily prove with a computer, right? So like the four colors theorem, which is like the first thing proved by a computer, it resulted in checking a ridiculously huge number of cases. Okay, so something like that, of course, computers excel at, but in many cases, a constructive proof about existence, doing it by computer would require, like a demonstration that this algorithm always works or something. And it's typically, like, this is not the sort of thing that's approached with the computer. So, like, why do people do this? The main reason is probably to test out various computing methods. So, some methods may be developed out of this. I mean, when it comes to computing, a lot of stuff that happens accidentally. It's because you were using, you develop something to answer a question that was totally unrelated. to what ultimately that thing was, used for. But these Hadamard matrices actually have some applications, and so having them, because who knows how long it would take to prove this, right? This is, I mean, there are conjectures that are very simple that are still unproven from like 2,000 years ago, right? Something like twin prime conjecture. So, there's no guarantee that a given conjecture will ever be proven. So, right. And I mean, it could even be wrong, right? That's why it's still a conjecture. It could be false, right? There could be some dimension that one doesn't exist for. And so in that case, well, it's just nice to have it's nice to have these larger and larger. So it turns out that there are arbitrarily larger and larger Hadamard matrices that you can generate through a couple of ways of constructing. So there's the Sylvester method and the Paley method that I was going to mention briefly next time. But anyway, so I'll get into that at the beginning of class on Friday. But Friday and Monday will be like glorified review sessions. So bring any questions that you have. I still haven't posted the reminder of what the final exam is going to entail, so I'll do that soon. So anyway, I will see you all on Friday. So bring questions about stuff, anything from the semester we'll go over.